We will start after 5 seconds, Jayanti ma'am.
Okay.
Yeah. My technical team are ready?
Yes.
Okay. Good evening. On behalf of Department of Microbiology, TN Medical College and Nair Hospital, I welcome to the second series From Dissertation to Publication Basic in Biostatistics. I thank faculty Dr. Nithya Gupta and all delegates who have taken their valuable time out to participate today. I will now invite Program Director Dr. Jayanti Shastri. She is a professor and head Department of Microbiology, TN Medical College and Nair Hospital, Mumbai, to give the introductory remark. Over to you, Dr. Jayanti ma'am.
Thank you, Sarika. A very good evening to all of you. Welcome to the series on dissertation to publication. As we are all locked up at home over the weekends, I thought we could make the most of it. And in addition, it is the centenary year of Topiwala National Medical College and B.Y.L Nair Hospital. So we have arranged this academic feast for you in the webinar series From Dissertation to Publication. Last Sunday, we had a program on literature search. We all have postgraduate students, and many a times we are in fact grappling in understanding what is the sample size. So next in the series is basics in biostatistics. As we all know that biostatistics provides tools and techniques for collecting data and summarizing, analyzing, and interpretation. It is not as simple as the definition. We are extremely privileged and fortunate to have Dr. Nithya Gogtay to speak on this very important and considered to be very difficult topic, that is biostatistics. When there is a dissertation topic, that is the first thing which we have to know. how much should be the sample size which is representative for any outcome? And many a times we find that our dissertation do not get published because probably somewhere we went wrong in the sample size calculation. Without taking much time, I wish to introduce my good friend, Dr. Nithya Gogtay. I think no program is complete without Dr. Nithya addressing the students and the faculty. She is the professor and head of clinical pharmacology at KEM Hospital, Mumbai. She is the former editor of Journal of Postgraduate Medicine. She is a former member of editorial board of the British Journal of Clinical Pharmacology. She is the current chairperson of Tata Memorial Hospital Ethics Committee, current chairperson of Hinduja Hospital Ethics Committee, and she also conducts special training in statistics for CMC Vellore and for NIH workshops. I think this is a very, very modest CV which she has asked me to share. And she has many, many more laurels to her credit. And let's all enjoy listening to Dr. Nithya. Over to you, Nithya.
Thank you, madam. Thank you very much. Yeah, I'll just stop my video and I'll start my...
I have to stop share.
Yeah, just give me a moment, please. Thank you so much.
Requesting all of you to please put yourself on mute.
If somebody could confirm that it's visible.
Yes.
Yeah.
Yes.
Okay. Okay, so thank you very much, Dr. Shastri, Riverroot Events. Thank you very much to colleagues from Nair Hospital. A lot of familiar, I wouldn't say familiar faces, but familiar names of people that I've worked with over the last 25 years. So thank you very much for calling me today. I think I should also say thanks because I really cannot fathom why 96 people would come on a Sunday evening at 6:30 and listen to statistics. So I think, madam, it speaks a lot to your leadership that you've already got so many people to listen to a subject which is so dry. So thank you sincerely for coming. Dr. Shastri talked about sample size calculation. This talk was initially intended to be a 2-hour talk, but I think what I'll do is maybe take it over 2 parts, Dr. Shastri, if you will permit. I'll come back a couple of Sundays later to close whatever I may have left out today. Because if you sort of take it in all in one stretch, then it's not a subject that you should do over 2 hours, and especially on a Sunday, okay? So let me just go ahead. 1 second. All right, so I'll start with this particular quotation that was published in the American Journal of Surgery in 1990, 10 Rules for Reading Clinical Research Reports, that a fellow with one leg frozen in ice and the other leg in boiling water is on an average comfortable. This was written by the then editor, Dr. J.M. Yancey. And unfortunately, this is how most clinicians actually tend to view statistics. But what I'll try and do over the next 1 hour or so is to try and tell you it's not really that difficult once you figured out some of the nuances of it. So what I will be talking about is essentially why we need statistics. Why do we need to understand statistics? The concept of variation and probability in medicine, sample versus population, numerical versus categorical data, parametric and non-parametric data, distributions, and I think perhaps something which many of us still grapple with, and that is confidence intervals, a bit of problem solving and summary. The way I do these statistics lectures or workshops is really to give you the problem and ask you to solve it. Now, these are not possible on this particular virtual platform. So what I'll do is I'll answer the problems. I'll give you a little bit of time to think it through. I'll answer the questions myself, and you can, sort of take a call as to whether you got the right answer. And if you didn't, that's still all right, because we're all learning as we go along. Okay. So let's first start with why do we need statistics? And we need statistics, and I think all of you will agree with this, that variation characterizes much of what we do in medicine. let's take the example of lung cancer. Now you have smoking and lung cancer. All of us know that smoking is associated with lung cancer, but you will have people who are non-smokers also developing lung cancer. So one example of variation in medicine. Another example is, this is now I think several years back, and this happened at the JJ Hospital, that you had an intern, or I think it was an MD student, who went to take prophylaxis benzathine penicillin. She had been taking routine benzathine penicillin prophylaxis and actually collapsed and died of anaphylaxis. So again, differential responses, another example of variation in medicine. The third example, if there are some pediatricians who are listening in, is differential disease symptoms. So for example, if you have an adult patient presenting with asthma, you'll have wheeze, whereas in children, you have something called as cough variant asthma. So all of us, when we practice medicine, I'll give you an example here. Let's say you have a patient who walks in. This patient has a history of chronic smoking for the last 10 or 15 years, right? And he presents to you with weight loss. He presents to you with chronic cough. So what do you automatically think of? You think of the risk of CA lung or CA esophagus due to the exposure. So what do? You write a series of investigations down. You ask him to get a CT and MRI. And while you're waiting for the reports to come in, what do you say? What is the probability that the patient has CA lung, CA esophagus? And once you have a diagnosis and a diagnosis is come in, and then you start planning chemo or radiation surgery, what you start thinking about is the chance of cure. So with the same patient, what are the three statistical terms that we are dealing with? We are talking about risk, we are talking about probability, and we are talking about chance. So remember that each and every one of us, as clinicians, as people of medicine, we think in terms of statistics, whether or not we realize that we are thinking about statistics. And that's because diagnosis and treatment are essentially based on probability. And yet it is very difficult for most people to grasp statistics. And why is that? That's because oftentimes terminology does not make sense. I'll give you three examples here. The first word is significance. No, significant. When you say statistically significant, it is different from the way we use the word significance in regular English. So when we say significant, it's something important. However, when you use the word significant in statistics, what you're really saying is A is better than B, surgery is better than medical management, or this diagnostic test is better than this diagnostic test. The second thing is error, right? Error in regular English is a mistake. Whereas here, when you talk about error, you're talking about something called as an alpha error, which is a false positive error, and a beta error, which is a false negative error. And then you have hypothesis and so forth. So terminology doesn't make sense. It also, whether we like it or not, involves mastering abstract concepts. For example, if I were to ask you, what is the equation of a line, right? Now, this is Sunday evening, it is 6:45. So you start wondering, now, why should we bother about the equation of a line? So the equation of a line is essentially y is equal to mx plus c, or y is equal to ax plus b, depending upon how we were taught in whatever, 6th standard or 7th standard. So when I say y is equal to mx plus c over the next maybe an hour or so, you have to take it, right? That whatever Nitya Gupta is saying is gospel, right? So for you, for the next 1 hour, much of statistics requires faith, simply because I know that if I ask for a show of hands, a lot of you will say that you left mathematics behind so that you could get into medicine. But whether we like it or not, statistics lies at the interface between mathematics and science. And as the saying goes, what goes around comes around, right? So whatever you left behind will always come back and haunt you. And that is why you're listening to me today, right? There are other problems with statistics. It is difficult and frustrating for students as a discipline. But please remember that it is also difficult and frustrating for instructors. And I'm talking about myself today to get across a vastly complex and difficult issue, right? And this is again evidence that hundreds of thousands of undergraduates and postgraduates across a variety of majors, including are actually required to take statistics, and it is believed that most of us are not mathematically inclined. I don't know if we are not mathematically inclined or whether mathematics was not taught to us. I mean, I had a very I don't know what's the word to use, very not nice mathematics teacher and a very nice physics teacher, right? So I actually did very well in physics, but not in maths. But I think it's also how statistics is presented to you or how mathematics is presented to you. And the best way, I think, if you can connect with mathematics or statistics is to see how beautifully you see statistics in day-to-day life. And I'll give you some examples of that, right? And the other thing is 50% of what you learn about therapy, we go through this, right? There are so many paradigm shifts that have happened in medicine, but yet you need to go through all of them, right? Despite the fact that 50% of what you learn today may be wrong in the next 5 years. Right now, I've finished all the pontification and the philosophy. What I'll do now is to get into the core of what I'm supposed to talk about today, right? And we'll start with the first part, right? And that is population. So the fundamental reason why we do population statistics is to make this distinction between population and sample, right? So let's take the example of population. Responses of all participants attending statistics workshops in India as to whether or not they have consumed alcohol in the last 1 month. So this is my research question. I want to find out from participants who are attending these kind of workshops all over India, dissertation to publication workshops, as to whether or not they have consumed alcohol in the last 1 month. And this is my research question. Now, how easy or how difficult is it to answer this research question? Now, there are a lot of problems in this research question, and it is not just about whether we're going to tell the truth about alcohol intake, but it goes much beyond that. What are the problems? First of all, you need to put together a list of all participants who attend these kinds of workshops. So that's, you need a lot of resources for that. Second, you have to have the time, right? So you want to call up people, you want to, get their responses and put them together. So logistically, it is extremely difficult to answer this question because you want to ask this question to each and everyone who's attended a statistics workshop, right? So what do you do instead of that? And there's another component, which is ethics, which I shall come to in a bit. I talk to this captive audience that is listening to me, whatever, 9,600 odd students, and I ask them whether or not you have consumed alcohol in the last 1 month, okay? So what have I done? I have taken a small captive sample and they become representative of the population in which I intend to answer the research question. I do not want answers in the chat box. What I'm trying to tell you is when I take a small sample and I answer the same research question, I will end up extrapolating it to the population in whom I'm interested in finding out the answer to the question. So to give you some more examples of population, employment status of all employable people in the city of Mumbai, or blood pressure status of all urban Indian males. If we were to look at these same examples in samples, I will stand outside Churchgate railway station and I will interview 2,000 people who exit Churchgate railway station and ask them about their employment status to answer this question. Or I will take a small sample of 6,000 Indian males from 6 metropolitan cities and look at the blood pressure to answer the question on blood pressure in the metro cities, right? So I have moved now from the sample to the population, from the population to the sample. So if we were to define it statistically, what is a population? The set of data, numerical or otherwise, I'll come to that in a bit, corresponding to the entire collection of units about which we are seeking information. A sample is a subset of the population from which data are actually collected during the course of a study. I'll repeat it. When you look at the entire set of data, the entire collection of units about which you're interested in answering your research question, that becomes your population. However, a subset of the population that you actually work with becomes your sample. Now, I have a slide here which shows you the entire population, and I have two circles here. Now, what are the one or two key messages that this particular slide is telling you? So you have this whole population and you have two circles. One is a smaller sample and the second is a larger sample. So the two take-home messages on sample versus population here is that the sample has to be drawn from the same population to which you intend to extrapolate your data. So you cannot draw the sample from outside this population, outside this green ellipse, and extrapolate it, right? It's like extrapolating data from a tertiary referral center to the primary health center. It doesn't work. The second is, the larger your sample, the closer you are to the population. Madam talked about sample size in her introduction. We cannot always work with larger sample sizes. We'll come to that a little later. But remember that larger your sample size, more likely you're to find the truth or find the answer to your research question, because it will come closer and closer to the population that's what you're interested in studying. So to summarize the first part of my presentation, in most studies, it is difficult to obtain information from the entire population. And therefore, we rely on samples to make estimates or inferences, which we then relate to the population. And that is why statistics is needed. Okay. And to summarize the first part, we discussed population, which is the entire collection of units, the sample, which is the subset of the population. Statistics is needed because it allows us to make strong, robust conclusions from limited amount of information. And statistics allows us to generalize our results, to extrapolate our results, make our results meaningful for policy. Right? So that's why we need statistics. Now, with that, I come to the end of the first part of the presentation, and I now move on to a bit of core statistics. But before that, and this is something that I have heard ad nauseum over the last maybe 25 years now. So all that is fine. This generally comes from clinicians. All that is fine, but do I really need to know biostatistics? And these are the questions which are generally, these are the things that people tell you. I don't want to do medical research. I don't want to publish papers. I don't want fame, glory, or money. That's the only thing which I find difficult to believe. But I do believe that all of us want to do our jobs well. Yeah, we do want to do our jobs well, right? Now, if you look at this particular slide, what does it show you? 75% of 59 articles in Transfusion contained an inappropriate statistical test or contained an error in calculation or interpretation. 19% of 145 articles published in the American Journal of Obstetrics and Gynecology contained serious statistical errors. These are older data, but you'll find new data which is similar. So what does it tell you? Each one of us today knows about EBM, right? Evidence-based medicine. So you open your Lancet or your NEJM or the British Medical Journal or whatever journal that is relevant to your field, you read an article, you find something in that article which is interesting, right? And something which you think will change the way you do patient care. You pick it up and you start using it. But if that article itself is seriously flawed, then you're doing a disservice to your patient by actually reviewing that article. So how would you know that the article is flawed? only if you have some working knowledge. Now, at the end of 1 hour, this is not to tell you that all of you should become statisticians. No, that's not the point. The point is to have a basic grasp of the subject so that you can read and review your literature better and find flaws in it better before you actually start applying it to evidence-based practice. Okay. This is a favorite slide from a friend of mine, Avijit Hazra from Calcutta. You have, I think of this normal curve that here as Mount Everest. Mount Everest is located 8,848 meters above the sea level, which is 29,000 feet. So at the end of my talk, you will feel that you're here, right? And then as you go down and go into your Sunday evening and Sunday night and get back to Monday morning to your medical colleges, right? You are back to square one, right? You have descended. What is the take-home message from this particular slide? Statistics comes with doing. And I'm not saying do calculations, but read journals, read articles, and figure out what they're trying to say in that. Okay. Now with that, I'll go to the second part of the presentation for today, and that is types of data. Everything in statistics really starts with data, right? And I would recommend here a small book. It is an orange colored book. It's called as Statistics at Square One. It is a British medical journal publication. It's available for 100 or 120 rupees. Since I belong to the hard copy era, I have multiple hard copies of it. It's a freely available book on the internet. Much of the presentation that I'm making today is taken from that book. What I like about the book, it is non-statistically written. It's written in regular English that people like you and I can understand, right? So the first chapter in that book actually talks about types of data. Data is broadly divided into two types. You have qualitative data and quantitative data, right? So let me just talk first about quantitative data. Whenever we ask the question, how much is the height of a person? How much is the blood pressure? How much is the weight? That kind of data is measured, right? It is quantitative. Therefore, it is called as quantitative data or measurement data. Because the answer comes back to you as a number, it's also called as numerical data. How much is the height? How much is the blood pressure? How much is the CD4 count? So this kind of data is called as numerical or quantitative or measurement data. On the other hand, data which answers the question, what type? What is the color of somebody's hair? How much is what is the quality? Not how much, what is the quality of somebody's pain? That kind of data, which has got a quality rather than a quantity associated with it, is called as qualitative data. Because qualitative data can be slotted, can be put into a category, as I shall show you in the next slide, it's also called as categorical data. So these are the broad data types that we are dealing with. Let's start with categorical data. The objects being studied are grouped into categories based on some qualitative trait, and the resultant data are merely labels or categories. For example, hair color, black, white, brown, red, and so forth. Opinion of a patient about his headache, mild, moderate, severe, very severe, right? So the data has a quality and you can slot it or put it into a category. Therefore, it's called as categorical data. Categorical data is divided into two types. Ordinal data. So ordinal starts with an O. Therefore, there is an order in the data. There is a method in the data. There is a gradation in the data. Mild, moderate, severe, very severe is example of ordinal data, whereas nominal data is unordered categorical data. each of which is further divided into binary data. That means when you have just two categories, and non-binary data when you have more than two categories. So let's take the example of data where there is an order, ordinal data. For example, first MBBS, second MBBS, third MBBS, intern, first year postgraduate student. Degree of illness, none, mild, moderate, severe, very severe. Blood pressure, hypotensive, normotensive, hypertensive. And binary data, which could be either nominal or ordinal, has exactly two categories. For example, HIV positive, HIV negative, smoker, non-smoker, immunosuppressed, immunocompetent, present, absent, and so forth. So binary data, either nominal or ordinal. On the other hand, the second type of categorical data is unordered data. There is no order in the data, and that kind of data is called as nominal data. For example, hair color, black, white, brown, red. Opinion of students, for example, about these workshops. You may be happy, you may be neutral, you may be bored, or you may be just wanting to get on. Smoking status, smoker and non-smoker. Yeah. Then the second type of data, which we discussed earlier, how much is the height, how much is the weight, how much is the blood pressure. That is measured data, numerical data, quantitative data, data that comes back to you as a number. For example, serum cholesterol, height, weight, blood pressure, age, even time taken by me to complete the statistics lecture can be quantitated, right? And therefore it is quantitative or numerical data, serum lithium and phenytoin levels. Just like categorical data was divided into ordinal and nominal categorical data, numerical data is divided into continuous numerical data and discrete numerical data. Now, what is continuous numerical data? I'll give you an example here. Let's say you take the example of serum cholesterol, right? So you measure serum cholesterol and find out the serum cholesterol is 200 or 201 or 202, fine. Then you have a very, very sensitive biochemical analyzer, and that tells you that the person's serum cholesterol is either 200.1, 200.2, 200.3, and so on and so forth. Then next year you have an even more sensitive analyzer. Then you say it is 200.01, 200.02, 200.03, and so forth. So what does it tell you? Continuous data is theoretically data where any value is possible as long as you have a fine enough or a sensitive enough measuring device. Theoretically, continuous data means that there are no gaps possible between the data points. Just to give you an example, cholesterol we've discussed, height, age, for example, you could be 30 years, you could be 30 years in 1 day, you could be 30 years in 1 second, 30 years in 2 minutes, and so on, right? So you have data where theoretically gaps are not possible between the data points, and these usually come from measurement. On the other hand, discrete data or discrete numerical data is data where you have only certain values and there are gaps between the data points. For example, if you say number of children in a family, you can have 2 children, you can have 3 children, right? Or you can have 1 child, but you cannot have 2.5 children or 3 and 3/4 children, correct? It means you have gaps between the data points. Let's say number of COPD or number of COPD exacerbations in 1 year. You can have 1 exacerbation, 2 exacerbations, 3 exacerbations, but you cannot have 2 1/4 or 3 3/4 exacerbations. So this is discrete numerical data where you have gaps between the data points or gaps between the values. Generally, discrete data are counts. You can count 1, 2, 3, 4. These are counts, right? So examples of discrete data, MMSE scores, people who may have joined the Zoom lecture late, you can count, no, 1, 2, 3, 4, whatever. Number of cardiovascular deaths in a ward, or number of pregnancies, or age. Okay? These are examples of discrete data. And before I go on to problem solving, two terms which we often use is parametric data and non-parametric data. Now, what is parametric data? Data where the distribution can be represented by the normal distribution, also called as the Gaussian distribution, right? And when you have continuous data, so if you can see this line, no, here, this is continuous, correct? So generally you have continuous data which follows this normal distribution curve, right? It need not follow it, in which case it becomes non-parametric data. Remember, these are theoretical distributions, right? So continuous numerical data, you can plot into this parametric or normal distribution or Gaussian curve. Whereas you have non-normal or distribution-free data or distribution unknown data when your data doesn't follow this Gaussian pattern. What I will do now is I'm on slide number 40. I'm going to just run you through some problems. Like I said earlier, this would have been a Q&A in a regular class. I'll give you some time to think over, and then I'll solve the problem myself and you can figure out whether you got it right. We've discussed so far numerical data and categorical data. Now these are questions on categorical data. I'll do a quick recap here. What is categorical data? Data which can be slotted into a category, yeah, and which has got a quality associated with it. Further divided into nominal data, which is unordered data, and ordinal data, which is ordered data, like mild, moderate, severe. So the first question is, number of episodes of disease in a patient over a year. Okay. Now, how do you have number of disease? You'll have, say, asthma attacks, 1, 2, 3, and 4, right? So that is discrete data. So this is not categorical data. Second, serum bilirubin. Now, how do you do serum bilirubin? You measure serum bilirubin. Therefore, it is measurement data or quantitative data. But serum bilirubin can also be categorical data. And this is very, very important. Why? Because if you say bilirubin is normal or bilirubin is high, then you're slotting it into two categories, right? So this becomes categorical data. And this is the most important take-home message from today's entire talk, actually. All the data, all the distributions, everything we talk about, finally remember that it has to answer your research question, correct? As it is most important that your research question is answered by the data and not the other way around, right? And why do we, sort of collapse? And the word in statistics that we use is collapse. Why do we collapse quantitative data into categorical data? And I like this example of, now, of course, we are on, Netflix and Amazon Prime and things like that. But before the pandemic, we would all, at least I would, because you want to see movies. I'm a huge movie fan. I have become a huge movie fan. So you have a Friday newspaper where you have a critic reviewing that particular movie, no? So what does the critic do when he or she reviews the movie, right? You have a 1 star and a 2 star and a 3 star and a 4 star, and rarely you have a movie with a 5 star. So what is that star? The star is categorizing that data. It is qualitative data. A movie review, remember, is qualitative data, right? So 1 star, 2 star, 3 star. So when you have 3 star or 4 star, what do? You decide to see the movie, correct? It makes you take a decision to see the movie. But if a movie has 1 star, right, then you may not see the movie. Similarly, with quantitative data, it doesn't matter to you whether the bilirubin is 7 milligram per deciliter or 17 milligram per deciliter. It is high bilirubin. You've collapsed it. Therefore, what do you say? The prognosis in that particular patient may not be that good. It helps you to take decisions when you collapse quantitative data into categorical or qualitative data. Okay. Then we come to gender. Continuous data. Bilirubin is continuous data to begin with, and then it is collapsed into categorical data for the purposes of decision making. Gender is categorical data. Remember, the gender is non-binary categorical data. 1 minute, this is stuck again. Yeah. Severity of hemophilia, mild, moderate, severe. This is an example of ordinal categorical data. Reduction in blood pressure after treatment with an antihypertensive drug. Remember that blood pressure is measured, measurement data. However, when you say high blood pressure and low blood pressure, that becomes categorical data. Again, for the purposes of policy or decision making. Continuing, now this is the next slide on numerical data. Number of episodes of disease in a patient in a year. Yes, this is numerical data. It is discrete numerical data. It's like number of children in a family. Serum bilirubin, you measure serum bilirubin. Therefore, it is continuous data, continuous numerical data. Gender, we discussed it earlier. This is the same slide actually. Gender is categorical data. Severity of hemophilia, again it is categorical data. And reduction in blood pressure after intraocular treatment, you measure, you quantitate intraocular pressure. Therefore, it is essentially numerical continuous data. Yeah. Now we come to true or false. Which of the following statements are true about ordinal data? Right? What is ordinal? Mild, moderate, severe, very severe. The data are discrete and can take one of many values. Ordinal data need not necessarily be discrete. When you use the term discrete, what we're talking about is numerical data. So this answer is false. Data are continuous and follow an ordered sequence. They follow an ordered sequence, yes, but they may not be continuous. So that's again false. The data are categorical. Yes, ordinal data is categorical data because you slot it into categories. The categories of response are ordered. Yes, mild, moderate, severe, very severe. So ordered. There can be only two categories of responses. No, ordinal data can be binary or non-binary categorical data. Now, select all the data that you think are nominal. Remember, nominal is unordered categorical data. Height is measured, so it is numerical data. Ethnic group, Asian, African, American. Yes, it is unordered categorical data. Therefore, this is nominal categorical data. Social class has an order, so it is not nominal. Age categorized as young, middle-aged, and old. Remember, age is actually numerical data. Means you measure it, no? 12 years, 13 years, 17 years, whatever. But now, when you make age as young, middle-aged, and old, it automatically becomes ordinal categorical data. Again, remember the take-home message, data is not sacrosanct. The data fundamentally and finally has to answer the research question that you set out with, right? So remember that always. Age in years is quantitative data, right? Either discrete or continuous, depending on how you look at it. Now, very quickly, before we move on to the last part, state true or false about data types. A nominal variable has categories which can be ordered. No. Nominal means nominal, unordered. So this is false. Quantitative data occur when the variable takes some numerical value. Yes, numerical, quantitative data, measurement data. An ordinal variable is a type of numerical data. No, an ordinal variable is a type of categorical data. A binary categorical variable can be either nominal or ordinal. Yes, that is correct. Finally, nominal data are measurements? No. Nominal data are categorical data. Measurement data are quantitative data. So this statement is false. More and more now in literature, what we see is those beautiful Kaplan-Meier curves going up and then they go down, and we are supposed to interpret those Kaplan-Meier curves. So the third type of data, which actually needs an entire session by itself, is called as time to event data. And I'll introduce the concept very quickly here. So when you have a mixture of quantitative and qualitative data put together, that becomes data which is called as time to event data. That's actually started in World War II, actually. It's got a very interesting history. And that is used for survival analysis. For example, time to pain relief from an analgesic, right? So time is quantitative. Pain relief, yes, no is qualitative. So this is time to event data. Time to clotting of a dialysis filter. Time to discharge from the hospital. For some of you who don't have piped gas in your house and you're still dealing with gas cylinders, like I was until last year, time to that gas cylinder getting empty is also time to event data, right? Or your light bulb fusing and you need to change it. So time to changing that light bulb is also time to event data. Again, like I said previously, if you relate statistics to day-to-day life, then it becomes far more enjoyable. Okay, and this is the last slide of the second part of my presentation, that the type of data. So why are we doing all of this? I mean, why have we spent the last 40 minutes discussing data type and distribution? And I cannot reiterate this enough. The type of data and the type of distribution in a study determines how you present your data. Is it going to be a box plot? It's going to be a box and whisker plot. Is it going to be a histogram? And the type of statistical analysis or the type of statistical tests that you will use to analyze your data. It is the type of data, so understand what data is it, understand the distribution, and automatically your tables, your graphs and figures fall into place, as well as which statistical test that you will use to analyze your data fall into place. Okay, so now we move on to the third part of my presentation, because I talked a bit about distributions, and I'll go through distributions and then we'll see whether there are questions and whether I should continue further. I have another part as well, part 4, but we'll see how it goes. So I'm going to talk to you about 3 distributions: normal distribution, binomial distribution, and something called as the Poisson distribution or the Bernoulli distribution. And similar to the previous data types, we'll do a bit of problem solving, right? So the distribution that we are mostly dealing with on a day-to-day basis is called as the normal distribution or the Gaussian distribution. So this is a continuous probability distribution. So continuous numerical data is often represented by this Gaussian distribution. It's attributed to this German mathematician Charles Gauss, who is anyway supposed to have plagiarized it from another French mathematician. But this is a bell-shaped curve is what we are interested in, which is symmetrical in the middle. So if you see this normal distribution, the center of the normal distribution, if you remember from your PSM, your mean, your median, and your mode, all of this come together here. 50% of the data falls on the right of the normal distribution curve, and 50% of the data falls on the left of the normal distribution curve. So it is a bell-shaped curve, and it is symmetrical in the middle. Now, one question that I often used to ask myself when I started reading and teaching statistics is, why is the word normal? Why, what is normal? Does it mean that every other distribution is abnormal? No, and the reason I realized it is called normal distribution is because it occurs in nature. It's something, so if you take a set of values of serum cholesterol and you put it together, it'll actually fall into this bell-shaped curve. It's a theoretical distribution. However, a lot of things in nature actually fall into this normal distribution curve. The other thing that a normal distribution curve actually tells us is this area under the normal distribution curve and the variability. There is a very nice article on how statisticians are not actually dealing with numbers, but they're dealing with variability with respect to COVID-19. It's a beautiful article which is available in this Human Vaccines project on their website. Do have a look at it. So when you're dealing with the normal distribution curve, let's say we are looking at, how long does an Indian live, right? What is the longevity? So it would be about 67 years or 68 years, right? So that would be the center of the normal distribution curve. However, you will have a lot of people who will die early, children, childhood deaths, and you will have a lot of elderly. We do have a lot of elderly population now. People who are living well into their 70s and 80s with good quality of life. So what we are interested in knowing is not just the center of the normal distribution curve, but we are interested in the spread or the variability of the data. And this spread of variability is given by standard deviation. How far away are individual data points away from the mean? And that's what this standard deviation tells you, right? So very quickly, normal distribution, this is a true or false. Normal distribution is the distribution of a variable which is measured on healthy individuals. The answer is no, because all of us not just deal with health, we primarily deal with disease. So remember that normal distribution applies to, it's a theoretical distribution, so it applies to both health and disease. Is skewed to the right? No, it is symmetrical. 50% of the data falls on the left, 50% of the data falls on the right. And next two I've not taught you. 95% of its observations are contained within limits defined by mean and one standard deviation. So if you go back to this particular curve, 65% of your data is captured in this mean plus 1 ST and minus 1 ST. 2 ST will give you 95% of the data, and 3 STs will give you almost 99% of the data. So when this question about 95% observations contained within limits defined by mean and 1 ST is false. And this, according to me, is again very, very important. Normal distribution is completely characterized by its mean. Remember, no, a normal distribution is characterized by mean and variability. So a normal distribution is characterized by mean and standard deviation. So remember, that's very, very important to present, whether it's your dissertation or whether it's your publication. Yes, it is a continuous probability distribution. Okay, now, if the mean of a normal distribution is 20 and the standard deviation is 5, then 95% of the data lie within which of the following ranges, right? So 95% means 2 SD, no? So standard deviation is 5. 5 into 2 is 10. 20 minus 10 is 10. 20 plus 10 is 30. So the answer is 10 and 30. So this is how you learn to deal with the normal distribution. This slide will answer, and this actually will tell you what happens in day-to-day practice of medicine and how things which actually look like the normal distribution may not necessarily be the normal distribution. So the question is, which of the following variables are likely, the question is likely, no? Likely to follow a normal distribution. The number of hospital attendances in a year in a sample of adults from the general population. So this is actually not normal because what we get in the hospital is essentially sick people. Survival times following a heart transplant. No, this is again not normal because you will have a lot of mortality initially earlier on and then it peters out. Ages of first-year medical students, again, no, they would be bunching here. What is really truly normal in this particular slide is heights of individuals in the population. Okay, 1 minute, there is a question in the chat box. Okay, Sarika. The second distribution is binomial distribution. So binomial distribution is essentially a yes-no distribution, right? It's a success-failure distribution. So there is nothing continuous about a binomial distribution. So whenever you research questions, so you say a drug therapy worked, a drug therapy didn't work. So you flip a unbiased coin, not that Sholay wala coin. So if you flip an unbiased coin, you either get heads or you get tails. So this kind of distribution is called as a yes-no distribution, a success-failure distribution. It's also called as a binomial distribution. And the Poisson distribution is something which models very rare events, uncommon events. For example, several years back, we had this tsunami which hit a lot of southern India. That is an example of something which airline crashes now very, very uncommon. Air travel is actually a very safe form of travel. So some distribution or this acute flaccid paralysis after the poliomyelitis vaccine. So these are rare events into susception after the rotavirus vaccine. So these are modeled by this Poisson distribution. Just give me a moment. Yeah. So now very quickly, state true or false. Binomial distribution is the distribution of a continuous random variable. No, it is false. Binomial distribution means it is not continuous. Bi means just two. So this is false. Is always symmetrical. No, it is false, because if you toss a coin 10 times, it is not necessary that 5 times you will get heads and 5 times you will get tails. You might get heads 8 times and 2 times you may get tails. So it is a non-symmetrical. It could be symmetrical, but it may not be symmetrical. It is used for making inferences about proportions. Yes, because you will have a numerator, you will have a denominator, and a numerator and a denominator will give you a ratio or a proportion. So the answer is true. Okay, and this is the last slide on distribution. Which distribution is the proportion of individuals with a disease who are successfully treated with a new drug likely to follow? What is the answer? You're either successfully treated or you're not successfully treated. Yes, no, success, failure. So this is an example of binomial distribution. Which distribution is the weekly number of car accidents on the Mumbai-Pune Expressway likely to follow? Assuming that this is a rare event, this would be a Poisson distribution. It could also be binomial, because a Poisson distribution is actually a variant of the binomial distribution. And which distribution is the weight of doctors in a hospital likely to follow? This is normal distribution. Yeah. Okay. So I have actually completed 3 parts. I have a message on my screen which says my voice is breaking. I have full internet actually. I have a backup.
No.
Also.
Your voice is not breaking. That's perfect. You can carry on.
Yeah. So ma'am, I finished 3 parts. There is a 4th part. Do you want me to go through it?
Yes, please.
Yeah. Okay. Are there any questions so far? You can put them in the chat box while I share screen for the last presentation, last bit. Everybody's confident. Yeah. So we'll end with confidence intervals. Yeah. Okay. 1 minute. Yeah. Okay. So this is, I will stop after this. This is the confidence intervals, right? Just something wrong with my laptop today. Okay, let's start off with this clinical question. Now, you have 3 different physicians who are dealing with a particular drug, which is leading to bleeding. So out of 14 patients treated with drug A by physician X, 3 patients develop gastrointestinal bleed. So the proportion of patients who develop GI bleed is 3 divided by 14, which is 21%. Physician Y finds that only 2 out of 20 patients treated by him developed GI bleed. So that is 2 divided by 20 or 0.1 or 10%. And physician Z finds that 1 out of 15 patients treated by him develops GI bleed. So that is 7%. So you have 3 different physicians, one of whom has GI bleeding rate of 21%, one of whom has GI bleeding rate of 10%, and one of whom has a GI bleed rate of 7%. So what happens? Remember that this 21% and 10% and 7%, okay? Today we are living, I remember, if you go to, I don't know what happens now, but I remember that we used to go to these seminars, and for some reason I found myself in a seminar long ago, which was a seminar of surgeons. And what happens in a conference hall, particularly if you have a conference which is going on in a 5-star hotel, you have all the oldies, they're all sitting in the front, right? And you have all the youngsters sitting right at the back and next to the food table. And you have those middle ones, who are sitting in the middle. Now, what happens is that if you have a presenter who says something and he says it, in my opinion, I did the surgery and I found that I have a 10% bleeding rate, you'll have somebody sitting right in the front with gray hair saying, in my opinion, the bleeding rate is 7% or something, and there'll be a nice mara-mari and everybody's just looking to head for lunch or dinner at that time. So what we need to realize in statistics, and this 21%, 10%, and 7% are what we call as point estimates, right? There is a point estimate, right? What it doesn't tell you, what a point estimate doesn't tell you, is the variability, right? We discussed variability. What is the variability? So the GI bleeding variability ranges between 7 and 21%, right? So you don't express it as a single point estimate, but you express it as a range or you express it as a percentage. So what is the philosophy of confidence intervals? What it really states, and this is, for those of you who are postgraduate students and listening in, please do not just express your values as point estimates. Remember that what we find is what we find. It may not be what somebody else will find. There is always uncertainty in medicine. So we need to express this margin of error, which we need to give the uncertainty associated with our finding. And this is called as confidence interval. Again, while I'll speak about confidence intervals, this is a concept which you will find difficult to understand. No matter how hard I try as a teacher, this is something you will have to figure out for your own, right? So I'll give you the statistical definition. The probability or the range that contains the population parameter is called as the confidence interval, right? So I'll give you an example and try and explain it. So how do we calculate this confidence interval? These are the steps in the calculation, but I'll lead you to the interpretation very quickly. Let's say you're doing a study where you're looking at urinary lead concentrations in 15 children given in micromoles over 24 hours, and these are the values. So what you do is first you find the mean, right? So you summate it and you divide it by 50. Then what you do, remember I said, how far away is an individual observation from the mean? So you subtract this. We used to do this manually. Now this will be done by your calculators or your computer. You summate everything to take away the negative value and you put it together and you divide it by the sample size, that is 50. This is called as the variance, the variability. And when you take the square root, because you have summated it by squaring it, you get the standard deviation, nothing but the variability associated with your value. This is the only statistical concept today I'll try and explain as best as I can. This is called as the central limit theorem. And this central limit theorem is central to the understanding of confidence intervals. Let us say there are 4 people, 4 different people who are doing the same experiment. They are looking at urinary lead concentrations in children. So each one of them will have different findings, yes or no? One person will have his own mean and his own standard deviation. Okay. The second person has a larger sample size, will have his own mean and own standard deviation. So we call this mu1 and SD1, and we call this mu2 and SD2. There is another person who works with a much bigger sample size, and he will have mu3 and SD3. And finally, you have a very, very sincere person who works with a large sample size and has mu4 and SD4, right? So what does the central limit theorem state? That if this is your entire population and you have multiple means, mu1, mu2, mu3, mu4, you put those means together, they will also form a normal distribution curve, which will have its own standard deviation, which is called as the standard error of mean. That's the best I can do on the Zoom platform. So the standard error of mean is what is used to calculate the confidence intervals. And this is the formula for the confidence intervals. I'm not going to go through the formula, but what I will do is to take you through the interpretation of confidence intervals, right? So I have an example here. The mean diastolic blood pressure, listen very carefully, I'm closing the presentation, but this concept of confidence intervals is important. The mean diastolic blood pressure of 72 physicians was found to be 88 millimeters of mercury. That's nice, no? With a standard deviation of 4.5 millimeters of mercury. Calculate the 95% confidence intervals. We won't get into the calculation, but this is it, 87 and 89. So what is important here is the interpretation of the confidence intervals. So listen to me carefully. In the population of physicians, so you have a sample of 72 physicians. Remember, I started by saying that from the sample, we move to the population. In the population of physicians, okay, the value of the diastolic blood pressure will fall between 87 and 89, 95% of the times. 2.5% of the times, the value will be lower than 87. 2.5% of the times, it will be higher than 89. So the confidence intervals in biology, in medicine, we use the term 95% confidence intervals. The range that contains the population value, the population parameter, 95% allow a margin of error. Yeah, can I go ahead? Yeah. Okay. And I think with the next couple of slides, this is actually a real life example. A financial analyst wanted to look at the mean annual return on mutual funds. A random sample of 60 returns showed a mean return on investment of 12%. If the sample standard deviation is assumed to be 4%, estimate with 95% confidence the mean annual return on all mutual funds. So I've done this calculation for you already. So you have the stock market, right? And you have a financial analyst. He's taken some 60 mutual funds. Maybe the stock market has 60,000 mutual funds. So remember what I said, sample to population. So he takes the sample of 60 mutual funds and calculates how much is the return on investment. And what you get is 12%, which is a point estimate, right? And then he calculates the uncertainty. He calculates the margin of error. So this is 11 and 13. So again, I'll interpret it. In the population of mutual funds, not the sample, population of mutual funds, the return on investment will fall between 11 and 13, 95% of the times. 2.5% of the times you will lose money. 2.5% of the times you will make money. That means it will be more than 13% return on investment. So what I'll do now is just to drive home the point, I'll just end on a lighter note because I'm sure there's been too much of numerical data thrown at you. So recently you have a surgeon here, right? I hope no surgeons are listening in, who has a mortality of 60% for a heart surgery in children who are less than 1 year old, right? And you are the dean or the director. And the question is, would you sack him? What is 60%? Point estimate, right? What do you need? You need confidence intervals, right? So you say no, because you need to know the confidence interval. So you need to know the rate of other surgeons who are doing similar surgeries, right? So you look at the data in India and you say that the mortality for this less than 1 year children is about 27%. And this surgeon has a mortality of 60%. So will you sack him? No, because you still don't have 95% confidence intervals for 27%, right? So, and also remember that he may be operating on more severe cases. He may have done only 3 surgeries, right? And then just plain unlucky, and therefore his mortality is 66.7%. Then you have finally, there is no evidence. The surgeons actually operated on 15 babies, 9 of whom have died. The lower bound of the 95% confidence intervals is 19%, the upper bound is 36%. So this 60% does not fall between 19 and 36%, correct? So will you sack him now? Yes, but he is related to so and so and so and so and so. Yeah, so you can't sack him. Yeah. So life is a lot more than variability. That's what I wanted to end with, right? And this is a slide which I use very, very often, and something I'm really, something that's really touched me. This came in National Clinical Practice Urology, that a mistake in the operating room can threaten the life of one patient. A mistake in statistical analysis or interpretation can lead to hundreds of early deaths. So perhaps it is odd that we allow a person to conduct surgery only after several years of training, but give SPSS to almost anyone. Yeah. So with that, I think I'll close my presentation. I'll take a quick look at the chat box. I'll stop screen sharing and maybe take a few questions. Dr. Shastri, thank you so much again for inviting me today.
Sam.
Ajay, but it's not a mistake.
Excellent session.
Pankaj, hi, nice to see you, Pankaj. Girish, thank you.
I think everybody has understood everything. Need much more to learn. Yes, of course. Every time I hear Nitya, I want to learn more. Like they say, dil mange more. And Nitya, you haven't kept up the promise. You're going to give us a separate session on laboratory-based statistics, because currently my request is always to Nitya is we are grappling with diagnostic tests which are not gold standards. So as we are moving on to molecular diagnostics, we have so many tests in which we have to only see the agreements. And you know how TB diagnostics has also evolved. And even with TB, I don't think you can compare even the recent molecular tests with culture DST. So with all these issues which we are facing in the laboratory, I think we would really request you to have a separate session on diagnostic kits and their evaluation. Kits more than diagnostic tests and their evaluation.
Screening and diagnostic tests, yeah.
Yeah. So interpretation of diagnostic tests, basically. What are the various ways in which, see current, I'll tell you in the context of SARS-CoV-2, what's happened. we had so many kinds of tests for antibody detection. And even you can't even talk about sensitivity, specificity, because I really don't know whether chemiluminescence, which is a known assay, which is very sensitive, holds true for SARS-CoV-2. I'm saying that because we attended a number of WHO workshops and programs where home brew assays in the US have performed better than chemiluminescence. So when that is happening, and then WHO sends us a kit, and says, please evaluate this, it's very difficult for us. We just tabulate our results and send it to them. But at my end, I'm really wanting to understand better how we can interpret these test results.
You're essentially talking, madam, about flawed gold standards.
I would put it as incomparable gold standard. In the absence of a gold standard, how do you evaluate these tests?
Yeah,
is my question.
Tough ask, but yeah, I'll put together something. I'll
Yes.
do it. Yeah.
And you must give us one more slot of yours. I leave the time slot totally to you. We'll all be there. And on a Sunday evening, we had 126 participants. So that itself speaks a lot about Nitya, how people are just looking forward to listening to Nitya. Every time I listen to you, Nitya, I really go back enriched. And Dr. Dharap says, excellent, Nitya. Look forward to more sessions.
Thank you, madam. There is a question on sample size, but I'm wondering if it is sample size related to when you carry out a screening or a diagnostic test, because I think that would be the audience primarily.
Not necessarily. Whoever has asked the question can please clarify.
Because I can do that. I have so it is Dr. Jagirdar, in a dissertation with a limited period of study, would it be ideal to so I think all studies do need a sample size calculation. You must calculate the sample size. I think the difficulty that you have is that you're not able to execute the calculated sample size in your given time frame of 1.5 years or 2 years. Yeah, we'll have a separate class. I can do that sample size calculation. I'll work with you, madam, on a new date.
Yeah. So this happened even in COVID times. People had their sample sizes and they could not reach it because of lockdown and other things. And under the circumstances, even completing dissertations becomes difficult. But yes, this was a very good session, and hats off to you for making such a complicated topic simple. We never know enough about biostatistics, and it's a continuous learning. And once again, thank you very much from all of us. You're part of NCGM and you're part of our Nair Centenary celebration. And we look forward to getting another time slot from you.
Thank you so much.
Thank you very much.
Thank you. Thank you, one and all. Thank you. Thank you. Bye-bye.
Bye.
Thank you so much, all.